with that, we've got a CodeJoy, a special guest. We've got Diego Fonstad. So Diego, we are so excited that you're here. Welcome to CodeJoy. Thanks for joining us today.
Great, thank you. Excited to be here.
Excellent. And I'm going to invite Jeane on, and Jeane is actually going to be your interviewer today. So Jeane, you all ready to go?
Yes, I am. I'm here. I've got my mug and I'm excited to look at your space, Diego.
Excellent. Well, I'll turn it over to you. Have fun.
Wonderful. Well, hello, everyone. Hi, Diego. Why don't we just kick it off and I'll ask Diego, how you doing today? And where in the world are you currently?
I'm doing very well, thank you. I am in San Francisco, in downtown San Francisco, in the Mission District. So
that is so delightful. We're, of course, here, we're in Pittsburgh, CodeJoy. So we're quite far away from each other, but that's, the wonderful power of the internet that we can all be here together today.
yeah.
So in our interview today, we're going to talk about lots of cool things and lots of things in your space, but I think it'd be a good idea to just get everybody to know you a little bit better. So I'm going to start off by asking you maybe about the beginnings of your career. Where did you start off? What were you doing before you were makerspacing? And what are you doing now? What's your makerspace looking like now?
Yeah, no, absolutely. So I mean, I would say I've always been tinkering and making, and that's been consistent throughout, even though I've had a very varied career in management consulting. Was right after college. And then I, joined the first internet bubble and rode that one up and down, and then went to business school and started a biotech company. And then after that, I got involved in makerspaces because of my oldest daughter was at an all-girls school, and the head of school asked if I could help set up their makerspace, and so I became involved in setting that up. And it was a great experience for me, because it's one thing to be a parent with opinions, it's another thing to be the person who actually has to implement and try to figure out what these things mean and what it and how it actually gets implemented. And that was a very very powerful and very enlightening experience for me. And I was associated with Castellea School for many years. I started out as their first director of their makerspace, but we quickly hired someone else for that. And I took on the title of a resident tinkerer. And that basically meant I was working closely with teachers and defining ways of incorporating maker-based education into their curriculum. That was the approach we took at Castellea, which was not as a standalone class, but as something that was incorporated into curriculum. And some of that was practical. And I mean, it was a mix of practical and philosophical. When you bring in a makerspace to a school, after there's an established curriculum, you're fighting for time. And so if you want to get people in there without having a dedicated class, you have to convince the teachers there's value to bringing their students in, and there's value to doing projects at the space. And so that was our goal, of trying to convince them that it was worth it for them to take time out of their curriculum to bring it in and do this. And Lectrify really, and Imagination Supply Co. really came out of the frustration at the time of what the solutions were for electronics engineering and coding. And effectively, this is 2011, we started this. In electronics, there was throwy LEDs and brush bots. And then after that, it was Arduino. And so it was just like this, whoa, first off, you had these two tiny little, very basic projects, and then you jump to Arduino. And Arduino, as powerful as and amazing as it is, it has its challenges in a classroom setting. And the more you try to scale and implement it, the more you see those challenges, which is one of the reasons I'm so excited about the microbit, and why I decided in 2018, I started building products for the microbit, because I could just, having lived with and suffered with Arduino, I knew both its benefits and its negatives. But no, I mean, I've been doing this maker stuff forever. In college, I took a machine shop course. I found actually something the other day that I made in college. It was a machined bicycle pedal, clipless pedal, because I wanted to figure out, this is 1990. I wanted to measure the power output, the force of a pedal stroke, and to figure out the best way, like for a cyclist to have an efficient pedal stroke. And so I took the machine shop class. I found this old pedal I designed. This unfortunately was not the final design. I realized that the force sensors I was using could not elegantly fit in this, even though this looks cool. But honestly, the biggest challenge at the time was actually the interface for the data gathering. And so if I'd had an Arduino at the time, it would have been so much easier. I had to learn MATLAB and all these very elaborate other layers in order to capture basic sensor data in order for what I was doing. And it's not lost on me that now, like, 30 years later, there's pedal power outputs built into pedals now. I mean, that's like, it's amazing to see how this stuff evolves, both on the cycling side, but also on the electronic side. But I also, for me, it kind of highlights that when you are in this space for a while, you appreciate the improvements, just like, Arduino was very powerful improvement to how to program a microprocessor and was highly appreciated and added a lot of value. The microbit added that extra layer that made it that much more powerful in the educational setting. And when you're doing this stuff long enough, even these incremental changes are valuable because they make a huge difference for the eventual adoption. So
yeah, man, that is so wonderful and vast. And just to give everyone a little perspective on how long you've been tinkering, I think we need to look at this headshot. So I asked Diego for a headshot, and everyone normally sends like the nice little properly quirked chin adult picture, and Diego sent me this fantastic picture. Matt, would you shoot me to the top down? You got to see, this one's really good. I mean, just look at that adorable little kid with a hammer tinkering away on something, right? I mean, that is just fantastic. So you really have been tinkering for a very long time.
yeah.
Oh man. So let's dive into the microbit for a moment.
Yeah.
So you talk about many things, but especially the idea of like the tools that you used to have and how they've gradually changed over time. And I know a lot of times when we're doing workshops with teachers, we talk about how there are a lot of tools out there that were made for tinkering, right? Like the Arduino was made for tinkering, or the Raspberry Pi was made for tinkering, but they weren't made for classrooms. And that's where we really love the microbit, because it is made for a classroom. So what do you do with the microbit, and what do you like about the microbit?
Yeah, so I was, my arc in working with the microbit, I was developing another product, and I'm looking around to see if I have a sample of it, but that was very similar to actually what the Circuit Playground looks like now. It was an integrated Arduino-based chip board, because this was prior to the microbit being launched. But when the microbit came out, I quickly looked at it and realized that it had everything. From a manufacturing perspective, it was impossible to compete with. I mean, just once you do the breakdown of parts, and like if I were to try to make that at cost, I couldn't compete manufacturing wise with it. But then the other part is what you're described as it evolved, its provenance is education. And that makes a huge difference from the beginning. So, Arduino evolved for tinkering and for engineers, and it was game changing for that.
Yeah.
But it was, its provenance was engineers. So it has these quirks in it that engineers can appreciate. Whereas the microbit evolved, from the history of it, it was evolved from the ground up for educators. And you can see that in the little details that they've done. At the same time, as I describe it, the reality is, in order to cram so much into that little board, they had to do some shortcuts, to hit the price point. The original ones were like $12.99 or 12 something. Yeah. To cram everything at that price point into this board, they put some shortcuts in there. Shortcut number one was access to the pins. So it's easy to access 3 pins, but now if you want to access a lot more, you do need something with an edge connector. Shortcut number 2 was the kind of the way power was also managed through those pins, I would say, but it's not even a shortcut. It's just a reality. It really is like, to keep it in this form factor, this is what you had to do. So I started to observe, once I realized the microbit was so powerful and hard to compete with, I started to observe teachers that were using it. And I made mistake number one of a small business trying to come up with a new product, which was for better or worse, I observed the power users. And so I developed, my first product was focused on power users. And I observed that they were creating these very elaborately rat's nested piles of cables when they were using the microbit to power motors because it needed separate power supply. And when they were they had this, it became a lot of random cables and stuff. And so step one was like, how do I make it easier to connect things? Because that also goes to part of my philosophy of all these coding things is we talk about physical computing as a vehicle for teaching coding. And so it has to be this positive feedback loop. I build something, I like it, I want to make it better, I code more to it, maybe I tweak a little bit under the hood of the physical part, but on balance, you want the students spending more time tweaking their code. If your goal is to teach coding, you want the students to spend more time teaching their code and working on improving their code than on constantly troubleshooting the mechanics or the build. And that's another issue that I would see a lot with Arduino is you'd have this breadboard with wires everywhere, and God forbid a student would try to move it and one wire came loose, and you're just like, oh my gosh, which one was it? It's not working. And so that student who could have spent all this time tweaking and improving their code to make it do more and more and more is now spending their whole class period tracing their breadboard and trying to fix it. So that was, trying to address that is I wanted to, the first board, the bit booster is kind of like a Swiss Army knife for the microbit. It made it it had a built-in H bridge. It has a built-in relay. It has two I2C ports. It has easy connection for servos. It has built-in NeoPixels plus an easy connection for extending NeoPixels. It also had 3 AA batteries built into the back so that you could power the motors, but also get your 3.3 volts for the microbit. It did everything. It slices, it dices. It's great for power users of the microbit. But this is 2018 when I first launched this. And unfortunately, I started going around in the US and nobody had even heard of the microbit. So here I had this power user board for people who had never even met it. And so they didn't even, it was solving problems that most people didn't know they had. So that pushed me towards a smaller board, which was kind of like a riff on the Kitronic M-Power that I called Bit Buddy. So this one uses screw down terminals. It has a 2032 battery, super small form factor when connected, so now I can do wearables. I can easily power this. I have a fully powered microbit in a tiny compact form factor. Because it's, you'll see like the back, you could easily alligator clip to the pins. Because it's using a 2032 battery, it couldn't power a motor. So I got around that by building a solid state relay for powering other stuff. So one use case could be like toy hacking. And that became the next product that I did. And there's another one kind of in between there that uses an edge connector as small as possible called the BitBuddy Plus. And then a few years ago, last year, I was working with the folks at Make, and they wanted to have a custom board for what they were doing. And we did the Make-A-Bit, which was really kind of an evolution of these product lines in that the Make-A-Bit uses, if I pull this off back here without destroying everything. So the Make-A-Bit uses the edge connector, the 3 batteries, pins on the back. But one big difference is it doesn't have a lot of extra bells and whistles. It just makes it super easy to use the pins and to use the microbit. But it also has an engaging form factor. And that's something that I don't think you can underestimate enough, in that when a student walks in to a classroom and sees a bunch of these on the table, they think, oh, I've got to start doing coding today. When they see a bunch of these on the table, they think, hey, what's that? What does it do? And so it just, their mindset is different right out of the box, whether it's it's the form factor really changes how the students engage with the product. And so I've got the Makey bit, and then because that's clearly branded Make, I've got my own bit explorer, which is using the same form factor. And so the general rule is also, I would say, is everything I do is very much driven by kind of the Papert logic of the low threshold, no ceiling. So everything's got to be easy to engage with, but then have not hold you back. So how do I try to achieve that? I try to use easy, non-proprietary, universally acceptable connectors that anybody, any sensor, any bit, anything, it's easy to do. It's all very clearly labeled. You can do that. You don't need to buy anything special to work with it. You'll notice every one of my products, from my simple circuits to my simple logic to my coding ones, all have these holes in them. Those are basically from the beginning when I did my LEDs and LEDs and battery packs. I wanted to be able to grid out my circuit, and I had to decide, am I going to do English metric? What kind of grid would I want to do that's universally acceptable? And I went with Lego. And Lego is a great, it's small enough that you can embed and work with it with kids, and large enough that it's tactile for the kids' hands. And it's 8 millimeters on center, 5 millimeter peg. Boom. You can build that in Tinkercad. You can explain that to somebody, show them how to do it, and they can build something like this 3D conductive probe or something that's going to connect with it. They can build it in Tinkercad because it's a known spacing that you can work with. So
that is really, really cool. And it's so cool that people are asking some questions. So I'm going to pull a question from the chat. We've got, is there something special about the Microbit that you appreciate as a product developer that the average user might not see?
Well, as a manufacturer, I envy how much they crammed in there and at those costs. So, I mean, I definitely appreciate that this is selling for cost. I mean, you are getting a bargain. As a developer, it's interestingly, it's the same things I kind of appreciate. I see as a power user, you start running into little quirks. So, for example, on the bit booster, on the bit explorer, I have access to pins on the back, and I was limited in which pins. I couldn't access every one of the pins. I had to make a choice of which pins I was going to allow access to or not, because unlike the bit booster, which has like an array of all the pins on the back, on the bottom, I didn't have the space for it on this. But I made the decision, for example, to not use the microbit pins that are also used by the LEDs. And the LEDs they'll list them. If you Google, and I recommend everybody Googles and prints it out, the edge connector pinout of the microbit, because it's important to know what pin does what and how they're used. But a good chunk of them are shared with the LEDs. And what does that matter? Well, if you're using an edge connector that drops into a breadboard and you're using random pins, because I just happened to drop my wire there and I'm going to use that one, that's pin whatever. If it's shared by the LED screen, you might get weird stuff out of it. You might get weird responses. There's a few of them that are analog reads. Well, the LEDs are also used by the microbit as the light sensor. It's very clever design. Here I've got this array of LEDs. I'm going to use the fact that a diode can sense light and turn that as my light sensor. So there's no extra sensor. It's a light sensor. Very clever. Great. But that would affect that pin. There's a lot of things. Like when I first saw it, I thought there was a gyroscope in there because it could tell the angle. How is it telling the angle? It's actually using the accelerometer to tell the angle. Now it's clever. You're using the force of gravity to understand what angle, because you've got a 3-axis accelerometer. But what does it mean? Well, if you're a power user and let's say I'm putting it in this ball and I want to measure the angle of it while it's in the ball and I'm throwing it, well, now it's not going to correctly measure the angle, because while it's accelerating, it's calculating the angle incorrectly because it's assuming a stationary object when it's calculating the angle. Little quirks like that. I don't even know, I think V2 still has this, but the same PWM that makes the sound runs the servos. So you cannot concurrently make sound in servos. Few people run into that problem, but when you do, you're like, what's going on here? It's So they're very efficient. They're very it's very cleverly, very elegantly done. But the biggest other design thing is just the ecosystem, the MakeCode, the fact that MakeCode runs on any web-enabled device, the fact that this is a hard drive emulator. It's kind of like what made the what am I thinking? The Makey-Bit so the Makey so powerful. It's a keyboard emulator. It plugs into anything and it works. This is a hard drive emulator. It plugs into anything and it works. So those are kinds of design things that are powerful. Whereas Arduino, you've got to have the right driver, and God forbid your iOS updated overnight when you weren't watching, and then suddenly everything broke, and you've got to go back and peel back the layers of the onion and figure out what's going on, and spend time on forums and do your research as to what I have to do now. So yeah, there's so many, but I think it's design and it's stuff like that, but the ecosystem, the MakeCode ecosystem is incredibly powerful as well.
Yeah, these are a lot of really good points. I think that, when you start your ventures into making with, computer science tools like the microbit or anything else, you end up getting to points where you play with it long enough, you tinker long enough, you dive deep long enough that you do get into these weird little things. Like, I have attempted to use Raspberry Pi before with students and realized, like, we're going to need a whole sandbox for them to exist in, and we need monitors, and you need this, and like all these complicated things. And there is something really amazing about microbit where they tried to eliminate as many of those things as possible. But it's really cool to hear, from you as someone who's developing with this tool, that, there's still tinkering left to do. And, I feel like that's just really amazing and interesting.
It's incredibly powerful, but sometimes these limitations are, I don't know, it's like, for example, there's an amazing artist out of Norway who does music with the microbit, and he has designed a polysynth that works on it. But the only reason it's not in MakeCode yet is they can't do the emulate. They haven't generated the emulator in MakeCode yet for the synth engine to work. But I mean, it's like there's the power of it. It's the perfect, Papert, low threshold, no ceiling product, because you can do, there are limits, but they're workable. Once you understand them and you can work through them, it's amazing what you can get away with on this thing.
So we're getting more questions in the chat, and I think that they're leading us in the direction of seeing some cool stuff. So
okay.
You do a very unique thing. When you're making all of these boards and all these cool extensions and pins and all this stuff, you're not just coming up with these ideas and then shipping them across the world to be made somewhere else and then come back here, right? You actually are manufacturing these things in your space, which is, I think, something a lot of us don't comprehend when we think about buying this stuff. I go on and buy things for my classroom, and I don't think of like, oh, I could actually do this myself. But you are doing a lot of this in your own makerspace. So can you tell us about that? And then I'm sure that you have some things to show us as well.
Yeah, no, absolutely. So I would definitely, yeah. So, I mean, I think the same things that have driven changes in the makers world, like 3D printers is a good analog, that when I started in the makerspace world, the first Thing-O-Matic was coming out, and prior to that, you had to spend tens of thousands of dollars to get something that came close to approximating that. The same thing is happening in manufacturing in certain areas, in that there are components of the manufacturing process that have been shrunk and are easier to do and are easier, and that changes how you can approach the manufacturing process. And also there are elements of the internet where, like, PCB manufacturing, I used to do a lot of my work here in the US. I had this guy locally, but I also now do a lot of work out of China, and it's astounding how fast it can be. Within a week I can upload a program file and get my boards back and start working from there. And that just changes the workflow and the mentality. One of the things that's been incredibly useful, especially for a product like mine, which I do not make particularly complicated circuits. I make circuits that I want people to interact with in a special way. So when I first got started, the idea of just taking a simple LED and putting it on a substrate, and that was the circuit, was an LED on this thing. 99% of the time effort in there is actually designing the LED, the physical stuff that is not used. And that was almost like out of the headspace of a lot of engineers, because for them, a PCB is a practical thing. It is a conduit for making, and it's not actually part of the design. There's, in the time I've been doing it, the other cool thing that's evolved is that not only have PCBs been used as part of the physical product more, but the art on the PCBs has evolved dramatically. And there are people out there pushing the limits of it. And it's awesome because you now can do some really cool stuff. I mean, I just made, for example, a kind of challenge coin badge for somebody recently. Let's see if I can get this thing to work. Lights, I think it has, like, you've got the shininess, you've got that, and there's a light behind there, but I let the battery die on me. But you can, and I've designed, I can design art on these things. So like I can make this more interesting. My little, the piece that snaps onto the back of my Bit Explorer that powers motors is called the jetpack. And so I made it look like a jetpack in, from The Mandalorian. And it's like, okay, so now I can snap this onto the back, and now he's got a jetpack and he can power DC motors and stuff like that. So the PCB art, it's really a combination that I am not building particularly complex circuits. I am building accessible circuits. And that means that the iteration and the testing and the form factor is an important thing. So because of that, I've leaned heavily on a lot of the maker-based tools. Back when it first came out, it's Bantam Tools had the Other Mill. It was back then, it was Other Machine. And I used them because for me to do PCB that was not just a functional PCB, printed circuit board, but was actually part of the function, it was hard to even explain to people what I wanted. So I had to mill my own examples, but also that the iteration is so much easier. If I am designing something, shipping it off to China, waiting a week or two, getting it back, testing it, every iteration takes time. It costs, there's costs both in time and money that increase. And because of those costs, I'm less likely to try different ideas and to keep pushing it. When I have a mill here that I can just churn out, so like, this is this product, well, I could mill it and test it out, and I could try different sizes and explore different, okay, does this form factor work? Does this actually, and actually hold it and interact with it, and then say, no, I've got to bump this, do that, move this here. I'm not waiting the week or two, even a week is blazing fast from China, but it's a delay. It's going to delay my design process, and it'll hold me back from trying new things because I'm like, oh gosh, one more change. I'm good, and you see that in the classroom, and you see students. I think as teachers, when you're trying to teach in a makerspace, one of the things we'd love to see is students iterate more and test more, but they rarely do. They often get on a track and they will defend their decisions to the death because they're like, oh, that's good, that's fine, I'm going to make this work, and we're like, why are they so pig-headed? Well, it costs them time to change, and so we have to find ways of making change lower cost in the design process. Whether it's like getting them to actually do a simple prototype up front that doesn't take a lot of work, a cardboard one, but even that, when I was teaching, we thought we'll do cardboard prototype first, then we'll laser cut this wood. But then we realized half the kids couldn't cut the cardboard fast enough, and so cutting the cardboard was taking them forever. And it was like, wait a minute, that's not working. But you have to constantly be looking, how do I lower the cost of iteration so that you actually get that in there? And that's the maker tools for me do that. I can 3D print, I can laser cut, I can mill, and a lot of the times it's just to hold it in my hand and be like, yeah, that's the right size, and now I'm going to do no, I want to nudge this or do that. But like if I'm laser cutting something, I'm much more likely to nudge something a millimeter one way or another and try it that way. then if I send it off to China and I got to wait another 2 weeks to nudge it a millimeter, I'll be like, yeah, it's probably okay, you know?
All right.
So
So Diego, will you take us on a tour of your space? So I know that you have tuned in on 2 devices.
I have,
Have
yes.
your phone handy. We're gonna spotlight your phone here.
So first let's see if I'm gonna try to mute me here on this one.
Yes. Yep. And then we'll spotlight there we go. Your space there. Look at that. We can see ourselves perpetually forever. All right, looks like Diego's working on getting himself unmuted on his phone. We'll give him a moment, but this will be really cool to see, what can manufacturing look like in a makerspace. The process that Diego uses to iterate upon these ideas and reduce that cost of iteration is really something that I think a lot of us strive for in classrooms. Like Diego was saying, kids don't want to wait to see things happen. And it's just a very relatable thing.
All right. I think I got the volume. I think we've got this figured out.
Yes,
So-
I can hear you and we can see what you're seeing through your phone.
Okay, so step number 1, I'm going to apologize up front. My place is an absolute mess, but I'll do the quick tour. This is my desk. This is my view out the window. This is now I'm looking down Market Street that way. You could maybe see the tippity top of the Bay Bridge, and on a clear day I can see the tippity top of the Golden Gate way over there. So I like to tell people I have a 2-bridge view, although it's not usually what they sell as a 2-bridge view. Over here are the laser cutters. I've got 2 epilogues. I really primarily use one, an epilogue mini, and this is my little light booth where I do my photographing and whatever. But we're going to walk into the actual workspace here, and here we go. And so first, I'm going to show the machinery used for making all the boards that use surface mount components. And so the process of making surface mount components, you typically so you saw the Bit Explorer before. You typically get these panelized on a board like this, and there's 6 per board. You then put it on these things that look like a big silk screen machine, and they are just stencil screeners that you put the solder paste on. You put the board there, you squeegee the solder paste onto it, and that puts the solder paste in the correct pads. This is the extra rolls of electronics and stuff. And then you get to the correctly named pick and place machine, which literally picks up the component and places it on the board. And if I kind of zoom in on here, each one of these has different sized components. These are rolls, these are tapes of reels of different components that just sit here on this machine. And the machine head here, of course, I put big eyeballs on it, will go around, pick up the component and drop it in the correct place. And this is another interesting part, is that all these machines, are similar to a 3D printer or to a laser cutter. I mean, you are working in 3 axes, X, Y, and Z. This one is coming, has to know where to go, where to drop it, and picks it up and places it. And this machine will put it there. It'll then get inspected over here. And that looks like a bagel oven is just a big reflow oven with a conveyor belt that you put it, once you've confirmed all the components are correct, you just drop it in here. And depending on the type of solder, the type of project, how long it takes between 8 to 11 minutes. It'll flow through here and pop out the other end. And you have your board with the components soldered onto it. A lot of extra stuff here. One of the things when you manufacture, you start to sometimes just packaging and everything. There's another ante room here, and then component storage. I also have over here a soldering robot. This is a robot that can go point by point and solder components. So that's for through hole components get soldered here. There are soldering stations over here and a nice big screen. And then on this Z rack, I have my mini print farm that has 3 mostly running all the time Prusas, a Z18, a little Prusa mini there, and a Creality that I end up using mostly for props and fun stuff. I haven't put that into full production yet. And then yeah, so that's basically the quick tour of the space. Are there any questions while we're in here?
There was a question from the chat. Well, before I say that, I have to admire the fact that you put giant googly eyes on all of your robots. Thank you. That makes me so happy. But someone asked, what tools do you use to build your devices? You know, you have some of these tools, but you know, do you use any, you know, tools you'd see in a typical classroom as well? I know some of these things I've seen in some different types of maker spaces, but what other tools are in there?
Yeah, so you know, it's interesting. So like, for example, as I pick up off the ground, like over here, this is something I cut out of on the laser cutter. And this was when I was doing some prototyping. I basically made a solder mask directly on the laser cutter. So a typical solder mask is you order it and it's made in stainless steel, and you can and it has like the cutouts of where the solder paste will go, and it takes time and cost to order these things. But sometimes I will just like do a temporary thing on the laser cutter or 3D printer where I'm just going to make a quick and dirty solution. I was doing those well, here's that that button I was trying to show you before, and hopefully this one will turn on for me. So like this thing required a solder paste on it, and I did a quick jig in the 3D printer. So this is still a laser, this is still ordered from China, but the jig that I do, and that's another thing that I use a lot of, 3D printed brackets and holders and things like that. The one thing I didn't show because I was like, had my back to it, and sorry if I'm walking too fast and it gets a little wonky here, but
We're doing okay so far, yeah.
This is the micro mill. I mean, this is the other mill that, I mean, now called Bantam Tools, and now they've got some other thing. They sent me a cover to try to rebadge it, but it fell off. That went there. Anyway, but this is, you know, this is incredibly useful. To be honest, when I was in the teacher makerspace, I never used the mill. The one thing I'll say about one thing I will say about teacher makerspaces is laser cutters and 3D printers are so nice because you don't have to think about the tools, you don't have to think about the paths, you don't have to think about the material. It just kind of works. But when you're milling, you got to think about that stuff, you know. I mean, it's the speed based on the material and how it's going to overheat it, and that's just a layer that can slow you down too much. I think I do a lot of 3D printing, and part of it is, let me go back to this one. And in production, so like over here is a whole bunch of feet. These are duck feet. These are kind of bird feet, and these, I call these bear. Oh no, these are the four-toed feet. And this is a bracket that I did. This is a Tinkercad connector that I did a simple tweak to, so that it can slide onto a PCB. And I have kits that are called Shake It that this slaps onto, and now, you know, it's part of this. When you anthropomorphize electronics, it makes them so much more accessible to students. So before I got smart and started anthropomorphizing the board, I would add feet and googly eyes to the boards to make them more accessible. And so and the other thing about this stuff in a school makerspace, small things print quickly. So take advantage of that. You know, you can make a lot of these, and I can fill up a bed, let it run overnight, and just churn these things out. And so I've got a lot of 3D printed parts like that. And I use them as part of production, which is slightly counterintuitive because I think a lot of people don't think of 3D printing as a logical part of production. You sometimes think, oh, I should immediately jump to injection mold or something like that. And yes, injection mold makes sense in certain places, but in certain ways, 3D printing works quite fine. So.
Someone asked, is there an art space in your makerspace as well?
I mean, define art. I mean, I guess this is, yes. I mean, I think it's kind of funny. This building is a converted mayonnaise factory that is actually mostly artist studios. And when they have open studios, I sometimes feel like I sometimes feel like I am like a imposter syndrome of like, oh, these guys are real artists and what I'm doing is very different. But at the same time, I've come to embrace you're getting creative, you're making things interesting. The making it interesting is art, and so I definitely have all the artist tools. I mean, as any makerspace should be almost indistinguishable from an art space, except that it has more electronics, and so I think that is what a lot of this stuff is this is tools for art and creating. And so I think it's no formal, like, I don't know, watercolor easels here and there, but otherwise it is an art space.
That's really cool. We have another question, and then we'll probably be wrapping it up after that to go to breakout rooms pretty soon. But someone said, how long does it take to make the Bit Explorer?
How long?
Yeah, how long?
Gosh. In terms of the actual manufacturing process, or in terms of like from design to finish?
Let's say the manufacturing process first, but then I am curious, like your design to finish, it probably took you much longer for that part, but the manufacturing itself, how long does that take itself?
It's an interesting question because I would say it's I chuckle at this because when I was in business school, one of the classes that always had very interesting math, but you never thought you would apply in real life, was operations. And here I am living it every day. It's hard to say for one unit, because once you are in production mode, you are sequencing many one after another, and they're going through the system. And so I think it's possible to, I haven't ever done like a full time tracking of it, but it's possible to do thousands a week. And just because once you get into the production cycle, you're batch processing these things. And so the biggest right now, one of the slowest rate limiting steps, for example, is the oven. This will take sometimes 11 minutes for something to get through. So then it's a question of, but then like, if you think from an operations perspective, if it's beginning to end is 11 minutes, but I can keep things going in there back to back, and I can get, I don't know, if I got like 1, 2, 3, 4 back to back. Well, so that's really, now I can think of this as really only 3 minutes to get through, because that's the time that's how often they're popping out the other end. And so then you start to, you go into that, like that Kaizen, you start kind of every component, you start seeing, okay, what's this, what's the bottleneck here? How do you tweak this? How do you do that? I mean, it really is this fun operations game if you want to geek out. So it's hard to say, because I don't think of it as how long one takes, I guess is why I'm hedging and answering that.
Well, that is really, really cool and quite amazing. And, a lot of these things that I'm looking at in your space do not look much different from things I have seen in Makerspaces before, and it's amazing to think the idea that, this is a reality in this current life that we live, that you really can make the things that you envision. You know, the things that you want to see are not out of your reach. They're not out of your range. And there's ways to do them. And there's ways to do them with students too. So,
you know, and it's fun to get creative. Like I actually bought this thing back when I was a teacher. This is a bread rack for and I still use pans from, you know, baking pans in here, but all my stuff is organized on this thing. I found it used at some metal scrap place. I painted it, and then I went out and ordered a whole bunch of baking pans, and now, you know, that and this 3D printing rack is a Z rack. You know, this is a clothing rack that I just tweaked with 80/20 and made, but I can roll it around and move it as needed. And this was also taken from a makerspace idea when I was teaching.
Mhm.
So all these things are directly transferable, I would say.
Yeah, it's this so cool. You're getting my brain going. We have a makerspace at my school. I'm like, oh my gosh, we could do such cool things. So you're getting me excited. I can only imagine that everyone else is just equally as enthused about all of these really amazing ideas that you have and seeing your space. So thank you so much, Diego.